This problem involves reasoning about assertions for a particular code fragment. We're asked to identify them as always true, never true, or sometimes true, sometimes false at various points in execution. And there are comments here to indicate point A, point B, and so forth. So our task is to fill in this table that involves two assertions. The first is that x is equal to 0. The second is that n mod 2 is equal to 0, or in other words that n is an even integer. And we're asked to do that for each of the 5 points in program execution to identify whether these assertions are always true, never true, or sometimes true. I've included the code in a JGrasp file so that we can take a look at this as we go through each of the different points in execution. And in a sense, we don't really have to know what the code does, but it's not a bad idea to spend a couple minutes talking about that. It's a mystery method that takes an integer n as a parameter. And what does it do with that n? It has a while loop that says while n mod 2 is equal to 0, in other words, while n is an even integer, set n to be n divided by 2. That takes away a multiple of 2 from n. And keep doing that while n is an even number. So keep dividing n by 2, take away another multiple of 2 until it becomes an odd number. What are we doing with x? It's a local variable that we initialize to 0. We increment it by 1 each time through the loop. So it's basically a counter that's counting how many times we go through the loop. Initially 0 because we've gone through the loop 0 times, but then the first time around this loop x becomes 1, the second time around this loop x becomes 2, the third time around this loop x becomes 3, and so forth. And then we return that x. So the method is returning a count of how many times did we have to divide n by 2 until it became an odd number. In mathematical terms, what we're computing here is the number of factors of 2 in n. Or another way of saying it is that we're finding the highest power of 2 that goes evenly into n. I've set up a little bit of testing code here that shows what value is returned by the method for the numbers 1 through 100. So we can go ahead and run this and see what we get. And we won't look at all of these values, but we'll look at a few just to get a sense. So you can see that for odd numbers, 1, 3, 5, 7, 9, etc., they all return 0. Every other one of these numbers is a 0. That's because those odd numbers have no multiples of 2 at all. 2 has one multiple of 2, 4 has two multiples of 2, 6 has just one multiple of 2, 8 has 3 because it's equal to 2 cubed. We can see down here that 16 has 4 multiples of 2 in it, so those perfect powers of 2 have some fairly high values. But 24 is a 3. That's because it has 3 factors of 2. It's divisible by 2 cubed, or 8. 32, we get up to 5 factors of 2 because it's a power of 2 that's equal to 2 to the 5th. And similarly, 64 gets us up to 6 because that's 2 to the 6th power. But we also get a pretty big reading for 96, for example, that has 5 multiples of 2 in it because it's a multiple of 32. So anyway, that's a quick idea of what this method is doing. But let's then go through and solve the different assertions problems. So we're asked to think about these two assertions, x being 0, n being even, at the various points in execution. So let's start with x being 0. At point A, this is right after the initialization of x as 0. So at point A, it just has to be true that x is equal to 0. So that would always be true at point A, that x is going to be 0. And what about n at point A? Well, all we know at point A is that we've called this mystery method and passed it an n. So is it an even n? Isn't it an even n? Well, it might be. It might not be. We saw that in the sample execution we had here. Sometimes we were passing an even number. Sometimes we were passing an odd number. So the answer here is that it's sometimes going to be even and sometimes going to be odd. So we'd fill that in with sometimes. All right, let's go to point B. And our first test involves whether or not x is 0. So at point B, is x equal to 0? It's tempting to say that we were at point A just before we were at point B. And we knew at point A that x was always equal to 0. So you might think that at point B it always has to be 0 as well. But remember that this is inside the loop. So you have to be careful to think about this. We may have been at point A just before being at point B, but we also might have been at point D. We might be coming around the loop for another time through the loop. So this answer about x at point B involves understanding what's going on at A and understanding what's going on at D. So in the table, I'm going to just fill this in with a question mark for right now, and we'll get back to that when we've looked at point D. In terms of n, this one is a little more straightforward. The while loop test says while n mod 2 is 0, while n is an even number, go into this loop. And if we're at point B, we entered the loop. The only way to enter that loop is if you pass the test, is if n mod 2 is equal to 0. So it will always be true that n mod 2 is 0 at point B. And we can fill in that part of the table, that it's always true that n mod 2 is 0 at point B. Point C involves what's true after we've divided n by 2. Notice that x does not change in value between point B and point C. No change at all in x. So whatever's true of x at point B is also going to be true at point C. So that's basically the same value. Whatever our question mark is, we'll fill in the same thing for each. But what about n itself? So here we divided n by 2, and our second assertion then is that n mod 2 is 0. So we knew that it was always true at point B, but now we've divided n by 2. Is it true at point C? Well, it might be. So suppose n was 16 at point B. Then it was an even number there. We'd divide it by 2, and now it would be 8. It would still be an even number. So it's certainly possible for n to be even at point C, but it doesn't have to be true. What if at point B n had been 10, which is an even number, and then we divide by 2, n would now be 5, which is not an even number. So we've got a scenario each way. And whenever you have a scenario each way, that would be sometimes. It's sometimes true, sometimes not true, that n is an even number at point C. Point D is after this increment of x. So let's look at x again. It starts at 0 and it's incremented here. And those are the only changes we make to the variable x. So if you think about it, you'll realize that x starts at this 0 and then always goes up. X goes to 1, 2, 3, 4, 5. It never comes back down again. So at point D, we know that x has to be bigger than 0 because it started at 0, and we know that we've added at least 1 to x. I mean, x has to be at least 1 by the time we get to point D, and it could be quite a bit higher because once x is incremented, it just goes up and up and up from there. So there's just no way for x to still be 0 at point D because that's after this increment of x. It started at 0 and then we've had at least 1 increment. So at point D, it just can't be 0. So at point D, it would never be the case that x is 0. In terms of n at point D, nothing has changed about n between point C and point D. So whatever answer was true at point C is going to be true at point D as well. So we'll just kind of bring that sometimes down. Now we're in a position to think about these two question marks. What's true at point B? And so remember that at point B, we were either at point A just before there, in which case x would be 0, or we were at point D just before we were at point B, because we've come back around the loop, and now we've gone from being at point D at the end of the loop, we come back around, now we're at point B at the beginning of the loop. And at point D, x is bigger than 0, always bigger than 0. So at point B, x might still be 0 because it's the first time through the loop, or it might be bigger because we've incremented x at least once. So those two question marks become sometimes. Sometimes x is 0 if the first time through the loop, sometimes not if it's one of the later times through the loop. So then we have point E. We want to think about what's true of x. Again, it's kind of tempting if you think about point E to say we were just at point D, just before E. We went from D to E. And it's certainly possible that that's the way things go, that we go from D to E. Now, we said that at D, x could never be 0. So that might make you think that at E, x could never be 0. But it's a little trickier than that, because we might never have gotten to point D. It may be that we initialize x to be 0, and then we were at this point A where x is 0, and we may have found that n was an odd number to begin with, in which case we never enter the loop. So we may have been at point A just before being at point E, and at point A x is 0. So maybe it's still 0 because it was just at point A before being at point E, or maybe it's not because it was at point D. So this is one of those cases where we have another sometimes. It could have been 0 if we never entered the loop, or it may be non-zero because we did enter the loop. But what about n mod 2 being 0 at point E? Here the loop again comes into play. We're saying here, while n mod 2 is 0, keep looping. As long as this thing is an even number, stay locked inside this loop. So the only way to get to point E, the only way to have exited this loop, is if this is no longer true. So it can never be true that n mod 2 is 0 at point E, otherwise we'd still be trapped in the loop. The loop says as long as n mod 2 is 0, keep going through the loop. So the only way to get to point E is if n mod 2 is no longer 0. So that fills in our final blank with never. N mod 2 can never be 0 at point E, and that completes the table that we were asked to fill out.